Hello YouTube. In every profession, there are things that can make life difficult. Real plagues, such as flower moths for a baker, rats for a butcher, rust for a car mechanic, or mites for a beekeeper. There is also such a plague in electrical engineering. I would even call it a real pest, which many people, in particular beginners, aren't aware of. In my opinion, this pest causes millions in damage every year and destroys development time and capacity. We are talking about the plague called common mode noise. I would like to use this video to draw attention to how dangerous and damaging common mode noise can be. Because many beginners are not even aware of what common mode noise is, which may destroy their assemblies, devices or components, causing them weeks looking for a strange fault, and often they never find out what actually caused the hardware to fail. First of all, we need to look at where common mode noise arises, mainly in switch mode power supplies. There are other sources, but switch mode power supplies are the #1 candidate for common mode noise. I have a typical switch mode power supply here. On the input side, the supply voltage, i.e. the mains voltage, is filtered, rectified and smoothed in one or several filter capacitors. This capacitor is also known as a DC link capacitor. The energy which is stored in this capacitor is then chopped into small portions and transferred, little by little, to the secondary side via an electrical transistor switch and a transformer. This means the switch chops at a very high frequency rate, ranging from tens of kilohertz to a few megahertz. It chops up the energy in this capacitor and transfers it bit by bit to the secondary side. The entire control process is handled by a switching regulator. And this switching regulator must of course know what is happening on the output side. However, the output side must not be electrically connected to the input side. It is clear that this side is the hot side, the primary side. And the output side must be safe to touch. That is why the two sides have to be completely galvanically isolated. The output side is monitored and fed back to the control side via an optocoupler. This means that in an ideal world, there is no conductive connection between the primary and secondary sides of a switch mode power supply. Unfortunately, the windings of the transformer are wound in parallel, resulting in a stray capacitance to one another. This means that parasitic capacitances are created here. These also result, for example, from the heatsink. There are stray capacitances as well. These stray capacitances, for example in the transformer or in the heatsink of the power transistor, lead to a limited reactive current between the primary and the secondary side. Now let's have a look at this current. This reactive current causes a common mode voltage on the output, which is referred to as common mode noise. Switch mode power supplies are available in a wide range of variants and types. I have two different ones here. One is a standard USB charger. The other one is a 12-volt plug-in power supply. Now let's take a look at the output voltage. As you can see, 12.1 volts, so the device works perfectly. So where is this dangerous common mode voltage I was talking about? The problem is that I can't measure the common mode noise when simply measuring the output voltage of this power supply unit. Instead, I have to measure the common mode voltage between one of the two output pins and earth. And since I'm currently sitting on a chair and with my feet touching the ground, my finger has roughly earth potential. The common mode noise is an AC voltage, so in order to measure it, I have to switch the multimeter to AC voltage range. Now it doesn't matter whether I measure the positive or the negative side of the power supply with respect to earth. I can do it directly like this. I connect one probe to the power supply and connect the other one to my earth potential. And as you can see, I have about 81 volts here. I wouldn't expect that at all. I mean, I would not have expected 80 volts to come out of a 12-volt power supply in any way. Well, it's a high impedance source and an AC voltage, and I'm only measuring it to earth, but it's 80 volts after all. Unfortunately, many power supplies are switch mode power supplies, almost all of them these days. And for example, also laptop power supplies. A laptop power supply is also nothing else than a switch mode power supply. Here I have a standard Surface notebook connected to a switch mode power supply to its original Surface power supply. And here I have a USB cable which I have connected to this laptop. Since the negative potential is also the shield of the USB cable, I now measure here the ground potential of the switch mode power supply, meaning the laptop power supply on this USB housing. And we saw earlier that if we measure the output voltage of a power supply, a switch mode power supply with respect to earth, then I measure the common mode noise. In other words, I now measure the potential here to earth. And we see a relatively high voltage level with respect to earth. This voltage is so high. I'm going to switch off the light here, that if I use a phase tester, I don't know if you can see it. Yes, I think you can see it well. If I use a phase tester to the ground pin of the power supply, then you can clearly see the neon lamp lights up. Would you have expected that? I have a normal standard notebook on the bench using an original unmodified power supply unit. There is a voltage present here, which is so high that a phase tester lights up. Of course, this voltage is of very, very high source impedance, which means that if I touch the other side with my finger, the phase tester turns off immediately because this reactive current is discharged to earth via my finger. In other words, I don't realize that there is a high voltage here, but you can sense it if you very softly, and I think many of you have already observed this, run this metal connector gently over your arm, you notice a tingling sensation. And that is precisely this common mode noise. The danger I would like to draw your attention to, let's assume I'm a developer in the automotive sector and I have a DQ card for some kind of data acquisition. And I want to sit down at the weekend and experiment with it. I take my office laptop and connect the USB cable to the sampling DAC card, which has a wide range of mixed signal and high-speed analog inputs. Then this is now our ground potential. That means if I measure any voltage now, I always measure it with respect to the ground of this device. But this ground has a difference in potential with respect to earth potential of around 100 volts. Likewise, my finger has roughly a potential difference of 100 volts to this device's ground. So if I now touch the analog input, let's assume because I hold the screwdriver and touch the screw of the analog input with the screwdriver, then I effectively apply 100 volts to this highly sensitive analog input without even noticing it. None of us would do that voluntarily. If you have bought an expensive module, or if it has been lent to you, nobody would think of applying 100 volts AC to a highly sensitive analog input. But that's exactly what happens at the very second my finger or any object at earth potential touches this analog input. Would you have seen this coming? Let's say I'm not a developer from the automotive sector, but a hardware and software developer for medical applications. And I use a programmer, a programming device, to program a specific microcontroller or application processor then you see one eternity later. Then you can also still see the same 100 volts directly at the output of my programming device. You can now imagine what happens when I hold a piece of hardware in my hand and connect this programming adapter to the microprocessor or the application processor. I hold the device with my other hand and approach with the programming interface connector. There is a voltage difference of 100 volts between the two devices, which can lead to the fact that at the moment of connection, either the programming device, is destroyed, and/or the target, like my application processor, another possible example. Let's say I am developing using an FPGA. This is not a special FPGA platform, but there are Stratix FPGA platforms for 10,000s of euros and more. So I connect this board to my laptop and work with it. As usual, the laptop works fine. However, an FPGA has high-speed inputs and outputs. That usually means really sensitive pins, some of which work with voltages of 1.8 volts. So now I have 100 volts on my finger with respect to the ground potential of this board. Just let me illustrate this again by using the phase tester here. I don't know if you can see that one eternity later. So as you can see, again around 100 volts relative to Earth. This means that if I now touch these IOs with my fingers, I apply 100 volts, admittedly of high impedance, to these FPGA pins. That can be enough to destroy the module. Another example. I work with a Raspberry Pi or with an STM32 microcontroller. Both are USB powered. Here, the Discovery Kit. or here, the Raspberry Pi. I could either use a standard 5-volt plug-in power supply, or instead, and maybe even more handy and convenient, I could also directly use the laptop's power supply to power the Raspberry Pi, since the laptop's power supply might also provide a USB output. As before, there's again the same dangerous situation. Again, there is a difference potential of 100 volts between Earth and the GPIOs. In other words, I just connect the board while holding the board's pin headers, and might have already damaged or destroyed an input. The same applies here. I connect the board to the laptop, and maybe also want to connect something to an analog input. Or I just want to touch the button and perhaps slip and touch some components here and accidentally apply 100 volts to the components in this area. In the vast majority of cases, everything's gonna be fine, nothing happens. But that's not always the case. In some cases, an input is then damaged or destroyed, and you wonder, I haven't done anything with the board yet, I also haven't connected any dangerous voltages at all. I haven't done anything wrong, yet the board is broken. The worst thing about this is that you don't get a feedback. There's no dedicated signal LED on the board that lights up as soon as the chip notices that something is wrong with one of its GPIOs. You simply won't be informed about it, and that's why you assume the board works perfectly fine, just because you didn't do anything to the board. For example, if one pin, let's say A3 or C4 or any other I/O of this board doesn't work, the first thing you do is thinking that you've made the mistake yourself and double checking the software. That is exactly the point I mentioned earlier. This can cause you to spend a week desperately scanning the code to find out why this pin isn't working. All the other pins work, so why this one doesn't? Then only after a week you realize it's not the software, it's the chip. The chip has been destroyed. Now in this particular case, let's say I'm a beginner and I have no experience. And I'm sitting there, I've got the module connected to my laptop. I don't get the idea that my board has been destroyed by my USB cable, because I know USB only operates at 5 volts, and I have connected my board in the correct way and as specified, either by using a mini USB in this case or a micro USB in that case. Therefore, there's absolutely no room for any thought that I've destroyed my module just by powering it from my laptop or my 5-volt USB power supply. You would not have seen this coming. That is precisely the dangerous thing about common mode noise. You simply are not aware of it. You are not aware of the damages it could secretly and silently cause, because one simply doesn't develop an awareness of it where dangerous voltages can occur. A fraction of a second is already enough time to damage your hardware. Now let's say I work in a sensitive area, an area where expensive hardware could get destroyed, but I ground myself using an anti-static wrist strap. I have a laboratory power supply here, I plug the earth connector in, and now I'm on the safe side because I'm earthed, right? Wrong. This earthing doesn't help in this case. If anything, it only makes things worse, because it potentially lowers my impedance to earth. We're not talking about electrostatic charges here, which is where this anti-static wrist strap would help, but a voltage to earth. This means that the better earthed I am, the more dangerous this voltage to my hardware becomes. The only easy and proper way to protect my hardware from possible high common mode voltage is to take the power supply and connect its ground output to earth. There are many ways to do that. either via a capacitor or via a direct connection to Earth. In other words, I would ideally use a terminal or a wire and connect it to this ground side and connect the other side to Earth. For example, I could take the Earth potential from a main socket or from the Earth socket of a laboratory power supply unit. Only then, when this side is connected to Earth, I no longer have any common mode noise and can work safely with my hardware. But there is a second possibility. I use standalone PCs. With a floor-standing PC, the housing is earthed, which it has to be. But the housing is also the ground potential of the USB outputs, for example. This means that there is no common mode noise with a standalone PC. So I can connect a USB cable and this point is earthed, directly hardwired to Earth. And there are no 100 volts or 150 volts with respect to Earth. Of course, this is also a certain problem if someone has been working with a standalone PC for years, using hardware such as Raspberry Pi or STM32, and never had any issues, never had boards damaged. Suddenly, the company says, you're in the field a lot now, take this laptop and you are able to do exactly the same things that you were able to do with your previous standalone PC. Everything changes. Suddenly, all the USB outputs on this laptop might carry common mode noise now. Suddenly, hardware could get damaged by these unknown voltages. I am absolutely convinced that components and hardware worth millions are destroyed worldwide every year precisely because of this common mode noise. Whether it's sensors, cameras, ICs, FPGA development environments, or programming devices. It can be anything. You can really imagine almost anything that could be destroyed by this common mode noise. And it's important to me to draw attention to this with this video. When I'm working with a laptop or with a plug-in power supply, then there's often common mode noise. This also applies to devices that use protective insulation. I have another example. If I have a device that is connected via such a razor-type connector, such as laptop power supplies in many cases, or PC monitors or some game consoles, then this device uses appliance class 2, also called protective insulation. This means that the device unlikely has a metal housing, but instead a plastic housing. Therefore, such devices neither can access the earth potential, nor can connect their output ground to Earth. So if I have a device that works with a plug like this, I immediately know that it most likely can't avoid common mode noise simply because it has no access to Earth potential in order to do so. This means that if such a device has an output, it is highly likely that this output or cables connected to it are heavily contaminated with common mode noise. Let's say I have a game console, for example, which is also supplied via such a connector, and at the back of the game console there is an HDMI output. I now approach with an HDMI cable coming from my TV or monitor and plug this cable into the console's HDMI output. For some reason the connector may already be a bit worn out, so the shield does not always connect properly. Let's say the shield connection gets interrupted temporarily. For whatever reason, maybe I have approached the HDMI connector with the HDMI cable at an unfavorable angle. So not all data pins are connected at the same time while the shield gets interrupted temporarily. Let's assume I'm connecting the console to a TV. The TV might be earthed or could also generate common mode noise. Let's say the TV also generates common mode noise because It is also connected to mains using this appliance class 2 razor type connector. Both might be even connected to different mains phases. So the two common mode noise voltages might be phase shifted as well, which could result in them being added up. Now in the very moment I plug in the HDMI cable into the HDMI connector, a voltage potential equalization takes place. Normally the HDMI cable shielding touches this metal housing first and everything is absolutely fine. Done, no problem at all. Now, like mentioned before, for whatever reason the shielding doesn't connect or gets interrupted. So this high voltage might be accidentally applied to the TV's data pins, destroying it or its input. Or destroying the source's HDMI output. I could easily talk about such cases here all day long. In the vast majority of cases where devices get damaged or even destroyed during the plug-in process, the root cause is a voltage potential equalization due to common mode noise. If, on the other hand, I have a device with such a connector, then the device has its own earth connection, its own earth potential access. In most cases, such devices come with a metal housing. These devices often establish either a proper hard or loose connection between their output ground and the earth potential. The best example is a standard ATX PC power supply unit. A PC power supply establishes a hard connection between this point and its ground output. This means that any common mode noise is immediately properly shorted and dissipated to earth. This is why the output voltage of a PC or PC power supply unit is clean with respect to earth. It was important to me to use this video to draw attention to the biggest plague in electrical engineering, called common mode noise. Please share the video, especially with beginners you know who may have projects just like this, working with an STM32, Raspberry Pi, DECU cards, or programming devices or whatever. If you know someone who works mostly with a laptop and with highly sensitive boards, please share this video with them. Maybe I can help one or the other to prevent expensive hardware from being destroyed. Thank you very much, and see you next time.